have limits of continuity, and so we look at the squeeze theorem. So the squeeze theorem, to use the squeeze theorem to find the limit as x approaches c of g of x, we need to know or be able to find two functions f and h that sandwich the function g between them for all x close to c. That is, in some interval containing c, the function f, g, and h satisfy the inequality. So basically, f of x is below g of x, and h of x is above g of x, and we're sandwiching g of x. So for example, f of x is this blue graph below, h of x is this red graph above, and in between there we have sandwiched this g of x graph. And the reason why we do that is so that we can actually find the limit as x approaches c of g of x, if we can't find it, if we can of the other two functions. So if we can find the limit at the f of x function and the limit at the h of x function, and we can say what they are, then we know that the limit at the g of x function has to be between those two, right?
What would be a situation where we couldn't find?
Well, hello. Here we are. Talk. So, we can use the squeeze theorem this way. Now, you could use a table of values, obviously, but this is just another method to go about it. So this here, this little f in your notes needs to be, if you still have it, needs to be gone. It shouldn't be there. So basically here you have, suppose the function f, g, and h have the property that for all x in the open interval containing c except possibly at c, f of x is less than or equal to g of x is less than or equal to h of x, and the limit as x approaches c of f of x, that lower bound function, and h of x, the upper bound function, both equal the same limit. Then you can say that the limit as that x approaches c of that middle one must be up. So if you can prove that the f of x one's limit is L and the h of x one's limit is L, well then the g of x one's limit is L because it's sandwiched between the two of them. Okay? So here we have, use the squeeze theorem to find the limit as x approaches 0 as x sine 1 over x. So we have, if x is, x can't equal 0, which it can't because we have an x in the denominator, right? Then g of x equals x sine 1 over x. So we're just saying that this is our middle function. This is that middle sandwich function. And it is defined. We need two functions that squeeze, sandwich, g of x equals x sine 1 over x near 0. Why do we need it near 0? Because they're asking us for the limit as x approaches 0, right? So if you want, you can type that into your calculator. Type in x sine 1 over x so you can see what it looks like. So x and then sine 1 over x. What mode do we need to be in calculus? Radian. So in our y equals, we have x sine 1 over x. So something like that. It's wonderful, isn't it? All right. If you look at it, though, there is no value in actually 0, right? It cuts it out. And it can't have a value at 0 because it would make our denominator 0, and therefore we can't have a value at 0. So, we say, since -1 is less than or equal to sine x, is less than or equal to 1. We know that, right? Sine x maxes out at 1 and mins out at -1. We know that. We know the graph does that, and it's continuous between those. For all x, we begin with the absolute value of sine x, sine 1 over x, is less than or equal to 1. And we know that x can. Now, why can we write the less than or equal to 1 thing beside it? And not sine x is -1 and 1. Yeah.
Because it's absolute.
There's an absolute value sign. Yeah.
Where did the x go? Like the first x?
We're just using this part. We'll bring the x back. It's part of the theorem. Okay. We begin with that. So we can have, I'll show it here so you can see it. So we have sine x, absolute value of sine 1 over x is less than or equal to 1. Now you just said the same thing, David. You said, where the heck did the x go? We need to bring the x back, right? We have to use just the sine function because we know that the sine function is between -1 and 1. So I can say that the sine 1 over x function is between -1 over 1, right? But you're saying the original has an x in it. We agree? So we're going to multiply this side by absolute value of x and this side by absolute value of x. So we do to one side, we have to do the other side. That's not something we can switch out. So now we have the absolute values conjoined. So we have the absolute value of x sine 1 over x is actually less than or equal to the absolute value of x. And then we can split it up. So we could go right, we can split the absolute value sign up and put it less than or equal to instead of one being negative, one being positive, so it's the same strategy doing that. Hitting the floor. So the absolute value causes you one negative, one positive. Wait a second, what are these now? F, G, H. Didn't I say I needed one function below it and one function above it? Now I can find the limit as they approach those. Yeah.
Do you still need the absolute value of x sine 1 over x?
You can technically get rid of the absolute value sign because we did the negative and the positive. Yeah. So we can go the limit as x approaches 0 of negative x, which is -0, which is 0. And we can go the limit as x approaches 0 of positive x, which is 0. Wait a second. So now the f of x is approaching 0. The h of x is approaching 0. So what can we say about the g of x then? It has to approach 0 because you squeeze it between those two, right? So therefore, the limit as x approaches 0, x sine 1 over x equals 0. Once I hit second year math, this is how it all looks, just so you know. Yeah.
But the original equation doesn't have the absolute value bars. So we didn't.
We can get rid of all the absolutes on all of these because there's absolutes in all of them. So it can just be, we can not write those two in terms of brackets. Because this can become, when we do this, we take this absolute, this can become like this, and like this, and like
Why
this.
do we write them like that?
With the absolutes. You had to write them with absolutes up here so that you got negatives and positives. because you get two cases with
So the
absolutes.
moment that you get the two cases with the negative.
You can
and
drop off the
positive,
absolute value signs.
Oh,
I should have put brackets, to be blatantly honest. And that's what you learned in grade 11. Like every single thing you learn in math, actually from 10 and up, because they're called pre-calculus, leads you to calculus. So that's why you learn about the absolute value piecewise functions and solving absolutes in grade 11. Because like I said, in grade 11, you could even have a quadratic, right? Like they had x squared minus 4x minus 5, the absolute value equals 6. And you get two cases, one where this was positive 6, and then you could drop it off one where it was negative. So the moment that you actually take the positive and negative case, you can drop the absolute value signs. It's a good question. And then here's the now try problem 5 and AP practice problem 11. Then we're going to go down to these ones. Basic theorems we already know. So we know that the limit as x approaches 0 of sine x is 0. Because on the sine x graph, what's your coordinate at 0? 0. It's 0, 0, right? And sine graphs are continuous, yes? So anywhere you pick an x, the y that goes with the sine x graph is the limit, because the sine x graphs are continuous. So our cos x graphs. We know that when we approach 0, which is the y-axis of the cos x graph, it's at 1. Cos x graphs are at 0 and 1. The maximum is on the y-axis. We know that. Sine x graphs are at 0, 0. Okay. A third basic trig limit that is important is the limit as x approaches 0 of sine x over x is 1. You don't believe me? Type sine x over x in your calculator. It's also in front of your face on your paper. Just. So the sine x graph as I approach 0. Oh, the board. Sine x graph as I approach 0 is at 0. Cos x graph as I approach 0 is at 1. And then the sine theta over theta graph, it approaches 1 from the left, and it approaches 1 from the right. So it is limit as x goes to 0. Now, f of 0 doesn't exist on that graph, right? You're now sliding sideways.
Yeah.
Okay. We're going to do example 2 and cos 3 tomorrow at the beginning, or example 3 tomorrow at the beginning of the class. So the only thing you have for homework is these two. And then we're also going to start derivatives tomorrow. And then we'll do practice questions again on Thursday, but we did a lot in the last 2 days. Tomorrow, and we learn about power, which is easy, there's no demand.